Okay, so welcome to Math 349, Operations of Order. This is, I believe, Lecture 20, Generating Functions. So for the rest of the semester, what I really want to do is I want to tailor the lectures to what will help you the most in writing either your chapter for the book or writing your math outreach. I want you to have two pieces of writing that you can point to with pride. And so if there is something that you would like to hear lectured on, let me know. Ideally, let me know ahead of time, but you can let me know at the start of class as well. Hey, Professor Miller, can you talk about X? I should be able to do that without any trouble as somebody who's been a professor for decades. But obviously, if you give a little heads up, I can then plan things a little bit more. Okay, so what I wanted to do today is talk about generating functions, because this will impact at least one person's chapter. It's also one of the most interesting, important areas of mathematics. There are so many things that generating functions can be used for. So where have we seen generating functions so far this semester? Fibonacci's. And so if I had a little bit more time, I might have actually put a little bit more on this, but Fibonacci generating function. And then one thing you have to be careful about is everybody has slightly different notations. We'll use f0 is 0, f1 is 1, fn plus 1 is fn plus fn minus 1. We'll define the generating function g of x, and we use a colon to indicate this is a definition, to be the sum, n goes from 0 to infinity, of fn x to the n. Do I have to start my sum at 0? Where could I start the sum? 1. They'd be the same function. So I'm just going to do this just for more general exposure. And we eventually showed, I believe, if memory serves, that g of x was, I think it was x over 1 minus x squared, something like this, I think. And from this, we wrote this as x over 1 minus alpha x, 1 minus beta x, right? And so we could write this really as x times 1 over 1 minus alpha x with some number a plus b over 1 minus beta x. And what did we use to get this? What does this remind you of from calculus? Partial fractions, right? Here is a use of partial fractions. If we try to expand 1 minus x squared as a geometric series, we would have the following danger. If we let r equal x plus x squared, then 1 over 1 minus x plus x squared is 1 over 1 minus r. This would be 1 plus r squared plus dot dot dot, which is 1 plus x squared plus x squared squared plus dot dot dot. And the reason this is so bad is if I want to calculate the x term, the x term is easy. It can only come from the x plus x squared. If I want to calculate the x squared term, it could come from the x squared in x plus x squared, but it could also come from x plus x squared squared. When I square that, I'm going to get an x squared. If I want to calculate the x cubed term, there's no x cubed from here. From x plus x squared squared, x times x squared is x cubed, so I'm going to get a 2x cubed from that. And then the next term is going to give me problems as well. So as a nice exercise, try to figure out what the coefficients are going to be. Well, of course, there's a trivial back way to do that. Expand it like this, using partial fractions. But try to do it directly by looking at higher and higher powers of x plus x squared. You could, if you want, pull out an x and say, look, this is x 1 plus x. This is x squared 1 plus x whole thing squared. This is x cubed 1 plus x whole thing cubed. You could do it like that. And what you can see is only finitely many terms will ever contribute. Great, it's a finite calculation, but that doesn't mean we can write down a nice closed form expression. If we use partial fractions, we can then expand it out. And when we use partial fractions, we end up getting that fn is 1 over root 5, 1 plus root 5 over 2 to the n minus 1 over root 5, 1 minus root 5 over 2 to the n. And this was Binet's formula. Any questions about this? So by writing it using partial fractions, we make it much easier to do this series expansions. As an aside, and I don't think we did this before, this is reasonable. Whenever you're doing math, you always want to try to do quick heuristic arguments to get a sense of, do I believe this answer is right? So let's look at the Fibonacci's. We know fn plus 1 equals, fn plus fn minus 1. Will you all agree that this is at most twice fn? The Fibonacci numbers are non-decreasing. There's that annoying 0, 1, 1 in the beginning where I've got 1 twice. All right, after that, they're strictly increasing. So clearly, if I replace fn minus 1 with fn, I've only made things larger. How can I replace 2fn? What's that less than or equal to? I'm sorry? Yes. But I'm sorry? Yeah, so say. But we know, but what do we know about fn? Right, so we just showed fn plus 1 was at most twice fn. So what would be true about fn? What could I replace that by? Nope. We showed that fn plus 1 was at most twice the term before it. So what's true about fn? At most twice the term before. So how would you say that mathematically? And so if we combine these, we now get fn plus 1 is thus equal to 2 squared fn minus 1. Now this is shampoo mathematics. Lather, rinse, repeat, right? So what do we know about fn minus 1? It's less than or equal to 2 fn minus 2. Therefore, fn plus 1 is less than or equal to 2 cubed fn minus 2. And so if we keep going, we eventually get to fn plus 1 is going to be less than 2 to some power either f1 or f0. Do you want to stop at f1 or do you want to stop at f0? f1, what's f0? 0. I'm not going to go all the way down to f0. That doesn't make sense. So I'll stop at f1. And let's think about what's going on. So here, 3 plus n minus 2 is n plus 1. 2 plus n minus 1 is n plus 1. The sum of the exponent of 2 and the index of n minus of f is always summing to n plus 1. So if I have f to the first power, which should my power of 2 be? Well, I don't think fn plus 1 is at most twice f1. That means fn plus 1 would be at most 2. So we said, fn plus 1 is at most 2 cubed fn minus 2. Fn plus 1 is at most 2 squared fn minus 1. So if you look at every time we decrease the Fibonacci number on the right, we increase the index by 1. So there's no change in the sum of the power and the index. So we have power plus index is always equal to n plus 1. So if my index is 1, what does the power have to be? It has to be n. So we know fn plus 1 is at most 2 to the n times f1, which is just 2 to the n. So we know the Fibonacci numbers are growing at most exponentially fast, and we know that that exponential base is at most 2. So that was an upper bound. What do you think we should go for next? And hopefully you heard the priming. This was an upper bound. What should we go for next? When you're writing, you can try to be kind to the reader and try to put in some key words to help them figure out what we should do next. Let's go for a lower bound. So, before we used fn plus 1 equals fn plus fn minus 1 is less than or equal to twice fn. Now we want a lower bound. So fn plus 1 is fn plus fn minus 1 what do you think that's going to be greater than or equal to? 2fn minus 1. So this is a little bit harder. Every time we lower index by 2, gain a power of 2. Okay? So we have fn plus 1 is greater than or equal to 2fn minus 1. So what would be true about fn minus 1? What would that be greater than or equal to? Two fn minus 3. And if we keep going on and on and on, we should get fn plus 1 is basically greater than or equal to I think we've got to worry a little bit. Do we have an odd power? Do we have an even power? So it's going to be like F2 or 1 down here. And now, if we lower index by, oh, sorry. What is the index plus the power of 2? Index plus power of 2 equals what? So here, 2 plus fn minus plus n minus 1 is equal to n plus 1. Oh, I'm sorry, I didn't explicitly write this. So this would be, so fn plus 1 is greater than or equal to 2 squared fn minus 3. Is the index plus power constant? So we agree index plus power is not constant, right? So let's rewrite things. I'm going to write this as the square root of 2 squared. Now, is the square root of 2 squared 2? Sure. So this would be the square root of 2 squared. So this would now become the square root of 2 to the 4th fn minus 3. Now is the sum of the index and the power of square root of 2 constant. So 2 plus n minus 1 is n plus 1. 4, oh, so I didn't change the exponent over here. Oh, no, that was right, because that's fn minus 1. That's fine. Fn plus 1 is now root 2 to the 4th fn minus 3, and minus 3 plus 4 is also n plus 1. So the index plus the power of the square root of 2 is equal to n plus 1. So this should basically be root 2 to what power? If it's supposed to equal n plus 1, and this is either a 2 or a 1, what should this be? Basically, it should be basically n minus 1, something like that. Maybe n minus 1. Something like that. And again, when you're writing something up, you have to be more careful. But just we can see that every time we do it twice, we gain a factor of 2, or essentially we're getting a root 2 every time we do it. So if we do it n times, we get root 2 to the n. So now we have root 2 to the n less than equal to fn less than equal to basically 2 to the n grows like r to the n for some r. So this is not a proof, but this is a suggestion. Just by looking at these extreme cases, we know it's growing faster than root 2 to the n. We know it's growing slower than 2 to the n. Maybe it's growing at the rate of r to the n for some r between the square root of 2 and 2. This is not a proof. Not everything in life has to be a proof. At the end of the day, it does. But right now, it's okay to gather some intuition to get a sense of what the answer might be. You know, a lot of times when you read a math textbook, you just have this chain of beautiful reasoning with no intuition at all as to where did it come from. How many of you have found that illuminating? Yeah. And if you found it illuminating, how many of you then feel like, yes, I could do something similar to this on my own? Right? That's the danger, is you can create something where I can follow what you're doing line by line by line, but I have no idea how I would do ever, something related on my own. And so what I want to do here is just talk about just getting a feel for what the answer should be. So I'm not surprised at the end of the day that I'm getting, 1/√5 times 1 times, the golden mean, to the nth power as the main term. That seems very similar to what I was doing before. You're trying to find some number r between √2 and 2. And can anybody tell me approximately what 1.5 the square root of 5 is? Yep. The square root of 5 is about 1.6. Yeah, I didn't know. I was saying square root of 5. Give me a lower bound for the square root of 5. It's at least 2. Give me an upper bound. 3. Okay, so I know this is at least 1 plus 2/2. This is at least 1.5. √2 is 1.414, greater than square root of 2. Square root of 5 is at most 3. 1 plus 3/2, that's 4. This is the number between √2 and 2. And I'm not using fancy bounds on square root of 5. Okay, we could get good bounds on square root of 5. There's no need. This is a very reasonable answer to get. And so what we can do is we can now use what's called the method of divine inspiration. I've mentioned this before in class, right? Yes. And what's the danger of this? You have to be divinely inspired. So let's guess that, Fn equals r to the n in Fn plus 1 equals Fn plus Fn minus 1. F0 is 0. F1 is 1. So then we get r to the n plus 1 is r to the n plus r to the n minus 1. So if I subtract, I get r to the n plus 1 minus r to the n minus r to the n minus 1 equals 0. We pull out r to the n minus 1, and we get r to the n minus 1, r squared minus r minus 1 equals 0. So either r equals 0 or r squared minus r minus 1 equals 0. Well, if r equals 0, what's the next solution going to be? What's r squared going to be? An r cubed. So if I just take r equals 0, it just generates an infinite string of zeros. So the really interesting case is when r happens to satisfy this relation. If we choose an r that satisfies this, then when we plug it in, it's going to satisfy the Fibonacci recurrence. So this is called the characteristic polynomial for the recurrence. So now, if we plug this in, we get r equals 1 plus or minus the square root of 5/2. And then what we note is we note linearity. If, an and bn solve the recurrence, so too does alpha an plus beta bn. So if I have a sequence that satisfies the recurrence, if I multiply every term by 17, well, it's linear. I would have the left-hand side would be multiplied by 17, and the two summands would be multiplied by 17. It's still a solution. So if I take r to the n, when r is one of these special values, this is telling me, try 1 plus √5/2 to the n and 1 minus √5/2 to the n. Both of those will solve the Fibonacci recurrence. I could multiply either one of these by any number and they would solve the recurrence. I could add and they would solve. This is very similar to a lot of things you've seen in linear algebra. If I have ax equals 0 and ay equals 0, then a acting on any multiple of x plus any multiple of y will also be sent to 0. So if two things are sent to 0, their linear combinations are sent to 0. And so now what you can do is you can just show by direct substitution that if I multiply the first one by alpha, the second one by beta, it's going to solve the Fibonacci recurrence. And then we choose alpha and beta so that we have f0 equals 0, f1 equals 1. So it's a nice exercise, you know. All right. Find alpha, beta such that f0 equals alpha 1 plus root 5 over 2 to the 0 plus beta 1 minus root 5 over 2 to the 0, and then do the next one when n equals 1. Okay. So you'll get two equations and two unknowns. And that will uniquely determine what alpha and beta are. All right. So these are the Fibonacci numbers. This is the simplest one to really work with. That is not too trivial. I could give you an is 2 to the n. You know, an is twice an minus 1. That's very straightforward. This is the first one that's a little bit more interesting. And so the question is, can we use this idea to solve other problems? And what I want to do is talk about something now that hopefully you have not prepared for class today, so that it is something that is new. I'm deliberately not going to say where these numbers arise from. Some of you may have seen them in another class. Okay. As a New Englander, what is the one thing I have to tip my hat off to New York City? The grids in Manhattan. Okay. So let's consider a grid in Manhattan or just anywhere in the world. And so I'm going to have, you know, some n by n grid. Not even going to try to draw 3, 4, 5. 1, 2, 3, 4, 5. And I want to look at all the paths that start at 0, 0 and end at NN. And you can only move east and north. Okay? So you can't move west, you can't move south. So I can't do some kind of strange loop. How many east steps do I need? I'm sorry? It's 5, but in general, I would need is n. And how many north steps? Also n. So the number of valid paths is what? So how many valid paths do I have where I start at the bottom left and end at the top right? Why 2n? Why n squared? What can you do if you're not sure what the answer is? Start with small cases, right? This should be your default. And say, hey, Professor Miller, rather than answering the question you want, can we do some small examples? Sure. What's the smallest n you want to do? Nope. 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 0, right? Let's build intuition. Now, sometimes, if you take things so small, you might actually build the wrong intuition because it might actually be a very different behavior. Sometimes the limiting behavior does not set in until later. I have a nice paper with Professor Goldmacher back when he was an undergrad and I was a young postdoc, where we were looking at something and we had an interesting process, and the first 7 moments agreed with the first 7 moments of the semicircle. And it seemed to be saying that the answer was the semicircle distribution. There was reason to expect why that might be the answer, but in the 8th moment, a deviation occurred. And it wasn't until you got up to 8 that there was enough space to move around for the obstruction to emerge. For smaller values, it just couldn't be seen. So absolutely build up some intuition, but be aware that maybe you're not seeing what's truly happening. So when n equals 0, we're going from 0, 0 to 0, 0. How many paths are there? I'm sorry. So this is where things that I would say there's one path, right? I'd say there's one way to do nothing. So that's why I'm saying we can put one in quotes right now as to we can have a legitimate discussion and a disagreement as to whether or not the answer is 1 or 0 here. I would agree that when n is 0, that you could potentially say there's one way to do it. That, or you could say there's no ways to do it, but because we've studied there's no paths at all. It is a sequence of east and north moves that get me from 0, 0 to 0, 0. And so let's see what the answer is, and then let's go backwards and see if it generalizes properly in here. I would agree that when n equals 0, we should definitely consider it, but I'm not confident there. Let's try n equals 1. So now we start off at 0, 0. We want to go to 1, 1. And so now the question is, how many paths do we have? 2 paths. So we can go east and then north, or we can go north and then east. Okay. Is this enough data to extrapolate? Oh, not even close. All right, let's do n equals 2. So now let's try to see how many paths do we have. All right. So give me one possible path. And I want to go through the paths in such a way that I don't miss anything. Good. So let's go east, east, north, north. So that's going to be, this path is 1. What's the next path? Okay, so I would say I like the idea of east, north, as my second path. East, north, east, north. What about my third path? I don't think I would do that one next.
East, north, north.
I think I would do east, north, northeast. So I think I would do east, north, northeast. What's next? I'm beginning to run out of colors, but all right, so now it's north, and then what was after north? East, east, and then north. So north, east, east, north. What would be next? Okay. Let's try maybe some kind of orange. Like this. So that would be northeast, northeast. And we have anything else? Okay, so then we would have north, north, east, east. So how many do we have now? 6. Okay. And again, it's very easy in a analysis like this to miss something. Did we get all the paths? Or maybe we could try to do some kind of symmetric argument. Half the paths will start with an east first, half the paths will start with a north first, right? There's a symmetry. So count the number that start with east and multiply by 2. And that could either be 2 factorial or it could just be excited. Either way is fine. Because by symmetry, I can flip about the middle. You know, flip about the diagonal. Right? So any path that starts off with east going first, I can flip it, and now it's a path that starts off with north. Conversely, any path that starts off with north, I can flip it and it's east. It's going to be a nice 1-to-1. I only have to do one of the 2. So there was no need to do all 6 of them. I only had to do the first 3. And now you can see why I was really careful about how I wanted to do them. I wanted to enumerate them in a very good, clear way. So we have to figure out the sequence 1, 2, 6, or maybe 0, 2, 6, or maybe we should get some more data. So for the next one, we would have to do a 3 by 3, but we know we only have to worry about starting off with an east, right? So let's try to think about what's going on. So here's 1, 2, 1, 2. All right, so now, and again, I decided to lecture on this this morning after emailing someone in the class, so this is not a lecture that has been planned. Let's think about this. Is anybody excited about enumerating all the possibilities? Okay, good. If you were, we were going to have a little private conversation, right? But there are certain points where we know how many paths there are from that point onward. So if I'm over here, how many paths are there from this blue dot to 3, 3? There are 2 paths. From this point, how many paths are there? 6. Right? So if I end up at this, let's not use blue actually, let's use a different color. So I can talk about green. So if I end up at this green dot, I know there's 6 paths once I get there. What if I end up at this yellow dot over here below 3, 3? How many paths are there? 1 path. What if I end up at this yellow dot below the yellow dot? 1 path. What if I end up over here? Also 1 path. So that helps a little bit. So what I could do is I could try to look at, how long is it until I hit the main diagonal? Because once I hit the main diagonal, I know how many more paths it's going to be. Or I hit the right wall. Once I hit the right wall, I know there's only one way to go from that point onward. So maybe do as hit the main diagonal or the right wall. And then double as doing an initial move of east. Okay, so let's think about what's going on. So I start off on my opening move, and I have to move east. If I now take a north move, how many paths will there be? 6. So east, north leads to 6 paths. What if I do east, east? So now I'm here. Well, then it splits, right? If the next one is north, I don't know yet. But if the next one is east, what do I know? 1 path. So if it's north, I now have 2 possibilities. I can continue to go north, or I could go east. So if I go north, how many paths are there from that point onward? 2 paths. If I go east, how many paths are there? So how many paths are there? Total is 10 paths. Multiply by 2, so 20 paths. So our sequence is the following. Here's n, and here's the number of paths. When n is 0, it's either 0 or 1. When it was 1, there were 2 paths. When it was 2, there was 6. When it's 3, there were 20. So now the question is, do we know any sequence that goes 2, 6, 20, or maybe 1, 2, 6, 20?
Is it 2 and choosing?
Ah, so we now have a conjecture. Okay. So conjecture, maybe 2n choose n. Well, when n is 1, 2 choose 1 is 2. When n is 2, 4 choose 2 is 6. When n is 3, 6 choose 3 is going to be 20. This is looking like a pretty good conjecture. It's got 3 data points that work. Then you could argue, what would 0 choose 0 be? I would argue it would be 1, because you would have 0 factorial over 0 factorial times 0 factorial. So I would say that the correct answer is going to be 1 and not 0. Do you think that this is 2n choose n? Seems very reasonable. And so let's prove it. Theorem. Number of paths from 0, 0 to nn moving east or north is 2n choose n. So the proof is the following. Is everybody familiar with n choose k? N choose k is the number of ways to choose k objects from n when order does not matter. Is everybody comfortable with that? So let's think about what's going on. 1, 2, 2n minus 1, 2n. We have n easts, we have n norths. We have to choose some sequence of easts and norths. So how many ways can we choose n of the boxes to be east and n of the boxes to be north? So there's 2n boxes, and we first choose n of them to be east. Choose n of the 2n to be east. We're now left with n boxes, make all north. How many ways can you choose n boxes from n to all be north? 1. And if you want to write 1 in a fancy way, nope. There were 2n choose n ways to choose n boxes from 2n. It's just n choose n. And so a lot of times when we write things, we lose the way to just look at the math because we drop factors of 1. But that factor of 1 is really there. This is just 2n choose n. Okay. So the number of ways to get from 0, 0 to nn on a grid is going to just be 2n choose n. Okay. As an aside, given that some people have had disagreements with me over how to count the number of ways to get from 0, 0 to 1, 1, what should 2 choose 5 equal? How many ways can you choose 5 objects from 2? 0. Do we all agree this should be 0? Yeah. So 2 choose 5 write as 2 factorial over 5 factorial, 2 minus 5 factorial. That's 2 over, anybody know 5 factorial? 120 times -3 factorial. And we want that to be 0. So -3 factorial is 0. So it turns out there is a way to extend the notion of factorials. And we would define the factorial of a negative number. Oh, I'm sorry, not 0. Sorry, not 0. What should it be? Not 0. It is, what would we need if we want this ratio to be 0? What should -3 factorial equal? Infinity. So the factorials of negative numbers should be infinity. The extension is what's called the gamma function. So gamma of s is the integral from 0 to infinity, e to the negative x, x to the s minus 1 dx. You can show gamma of n plus 1 is n factorial if n greater than or equal to 0 is an integer. You can show gamma of s plus 1 is s times gamma of s, which is why it's looking a lot like the factorial function. And the amazing thing is you get gamma of 1/2, which is the generalization of negative 1/2 factorial, equals the square root of pi. And this is actually extremely important in statistics and normalizing the standard normal. They're all connected. We often have to decide how do we want to interpret things in situations where they're not initially defined. And it's often useful to have a way to extend things. And so it's actually not bad to extend the factorial to negative integers and just define them to be infinity. It's not bad to extend it to other situations as well. Does everybody have a geometric sense of 3 factorial? What does 3 factorial represent? Okay, but give me a story. What would 3 factorial represent? Good. How many ways can I order 3 different books? I have 3 offices, president, vice president, secretary. How many ways can I assign the office's positions to 3 people? We all understand 3 factorial. Does anybody have any idea of what does it mean to talk about the number of ways to order negative 1/2 of a person? Right. We're now using this function in a very different setting. I no longer have the combinatorial interpretation. That only works if I have a positive integer or 0. 0 factorial is the number of ways to order no objects. How many ways are there to order no objects? There's one way to do nothing. What is the best TV show ever about nothing? Seinfeld. Good, right? It's the fixed point here. So let's go back to our problem. We now know the number of paths. What I want to do is number of paths not going above the diagonal. From 0, 0 to NN, using only east and north. Okay. So I have my grid again. And now, this is horrible. Oh, this is really bad. So here, with some generous bad eyesight, is my diagonal that I cannot cross. And I'm only going to consider paths that make it here that do not cross. Any path that doesn't cross is fine. And I say, well, always below. Because if I allow myself to always be above, I would just double. So I want to always be below, and I never want to cross the main diagonal. I'm allowed to hit the main diagonal. I could have something like this. I hit it, I move, I hit it again. That's fine. I just can't get above the main diagonal. Okay, can somebody give me an upper bound for the number of paths? You should be able to give me an upper bound immediately. 2n choose n, right? Be a smartass. We know the number of paths is 2n choose n. That's clearly an upper bound. Better upper bound. How can you make it a little bit better? Divide by 2. Right? Because we know that for every path that stays below, there's a path that stays above. They can just be flipped. We only need to look at half the paths. Okay, lower bound. 1. We know there's at least one path. Go east, go north. Do you think you can get n as a lower bound, or maybe n minus 1? So I start with an east, and then I look at, then I can do one north, and then I do all the east, and then do the remaining north. So east, and then in this block over here, 1 north, n minus 1 easts, and then over here we would have n minus 1 norths. So that would give me n minus 1 as a lower bound. With a little bit of work, you could probably get a lower bound of size n squared by saying, I've got 2 norths that I can play with. So maybe I start off with east, east, then I can put in 2 norths and n minus 2 easts, and then finish off with the norths. So as n gets larger and larger and larger, I can probably show that the number of paths is at least n to any power. Unfortunately, 2 to the n choose n is growing much, much faster. And so something which is wonderful called Stirling's formula that says n factorial is approximately n to the n e to the minus n square root of 2 pi n. So as an exercise, estimate 2n choose n and see just how big is that going to be. Okay, it turns out this is going to grow a lot faster than any polynomial. We can do something a little bit to get a quick estimate. If I give you x plus y to the 2n, this is the sum, little n goes from 0 to 2n, of 2n choose k, x to the k, y to the n minus k. So 1 plus 1 to the 2n is just 2 to the 2n is equal to the sum, n goes from 0 to 2n of 2n choose k. Thus, can somebody tell me why 2 to the 2n is an upper bound for 2n choose n? So why would 2n choose n be at most 2 to the 2n? So we use the binomial theorem. Is everybody comfortable with the binomial theorem? If I take x equals y equals 1, I get 1 plus 1 to the 2n, well, that's just 2 to the 2n, is the sum of 2n choose k, because x and y are both 1. So why would 2 to the 2n be an upper bound for 2n choose n? Why is 2 to the 2n an upper bound for 2n choose n? So I'm dropping every term but the term I care about. Are the terms I'm dropping, are they non-negative? Yes, when I drop them, I'm only making the right-hand side smaller. Right? So one term can't be more than the sum. If some of the terms were negative, then when I drop them, I could make things larger. Imagine you look at your personal finances, you owe me $1,000 and I say, I forgive you. Now I've dropped your term and your net value has gone up. So that's a upper bound. And we also get 2n choose n is going to be less than or equal to 1 over 2n plus 1, 2n choose n. And the reason for this one is you need to know a little bit about binomial coefficients. The largest binomial coefficient is the one in the middle. So if I replace all the binomial coefficients with 2n choose n, I've only increased the sum. And there's 2n plus 1 such terms. And so that gives us an upper bound. All right, so we will continue with this problem on Wednesday. And we will now, on Wednesday, see how we can use a generating function to actually come up with an exact count for how many paths there are. So this was the preamble to get us ready to figure out that count. If you want, before Wednesday's class, you can try to figure out, if you can, what is the number of paths that stay below the diagonal? Try to gather some small data and see if you can sniff out the answer. All right, let me stop the recording.